Hi everyone. So today's lesson I will be going through chapter 10, electrical circuits for OCR. This is the first lesson for chapter 10. I will be talking about how to analyze circuits in terms of series and parallel circuits, as well as a combination of them. So we have seen already two chapters for electricity, which look into some of the basic principles in electrical circuits, but this one is by far one of the most important chapters in terms of combining everything in terms of electrical circuits and how to analyze them. So what we will be looking at in this lesson will be Kirchhoff's second law. We will also apply Kirchhoff's first and second law to electrical circuits. We'll show how to calculate the total resistance when you have a series combination, total resistance when you have parallel combination, how to prove them as well. So these ones need a derivation, and you need to know I will show how we're going to derive it. Then we're going to have a look at how to analyze circuits that include both parallel and series parts of it, and how to analyze circuits with more than one source of EMF. Now we'll explain as we go through the lesson. So before I start, we know that there's a lot of circuits that we use every day in our single everyday life. So most of those circuits are not simple. So very rarely will you find a simple circuit of a series connection or a parallel connection. Maybe in tree lights, Christmas lights, they have, in the past they used to be connected in series, but now they're connecting them in parallel, which is much easier, and you understand why after this chapter. But usually most of the circuits that we use in our mobile phones, in our laptops, in our tablets, in the cooker, in the, washing machine, and so on, they have very, very complex circuit connections. And this chapter basically will help us understand how to analyze, no matter how hard the circuit is or how complex it is, there are a few basic principles that you need to know to be able to overcome that. And I will make constant mention of them throughout the lesson. So let's start first with Kirchhoff's laws and how they can be applied to electrical circuits. So a very quick reminder is Kirchhoff's first law, which we already saw in chapter 8. That was one of the first laws that we saw. So Kirchhoff said that the sum of the currents leaving a junction is always equal to the sum of the currents entering. Now, this law is based on the conservation of charge, meaning that no charge can be created or destroyed or lost or made in the circuit. So wherever charge is there, it's there. You cannot create or destroy charge. You do need to know that Kirchhoff's first law is based on the conservation of charge, which we already saw in chapter 8. And this is just simply an example here of having current going into a junction. So I in, using Kirchhoff's first law, should be equal. So the sum of currents going into a junction, if this is the junction bit there, so I in is equal to the sum of the currents going out of the junction. So I1 plus I2 plus I3. So in simple words, the total current going into a junction is always equal to the total current coming out of that junction. So this is a quick, some circuits here looking at Kirchhoff's first law. Here there is only one possible route for current to flow through. So obviously there's only one junction. So if I have 1.2 amps of current passing through this ammeter, that 1.2 amps will be same here as part of current, as current. The same current will be passing through here, through here, 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 so everywhere. There's only one root. There's only one junction. And there's no roots for it to split. So one single loop means simply that there's only one route for current to flow through. But if we have a look at this diagram here, you can see that 2.6 amps of current are heading towards this junction. So I have 2.6 entering. That means that certain amount should be exiting, the same amount should be exiting, but in two different routes. So as current heads to this junction, it gives it two possible routes to flow through. So that means that the 2.6 amps going in here will split in different amounts depending on what resistance each resistor has. I will mention that in a second as well. But you can see here that it says 1.4 amps go through this way. And then 1.2 amps go through here. If I add the two together, it gives me 2.6. So that's correct. 2.6 going in a junction and a total of 2.6 coming out of the junction. And then I would expect the same thing since 1.4 amps flow through this whole loop or branch. So I have another junction here. So I have 1.4 entering into that junction, 1.2 amps entering this junction as well. So the current going into this junction total will be 1.4 plus 1.2, which is 2.6 amps. And that means that the current exiting through here should be 2.6 amps. Remember, we always label conventional current, so it should be from positive to negative terminal, hence why we expect it to be looking like this in a direct current circuit. Then we go on to this one. It's quite similar as well, but in this case we have it splitting up more and more junctions. So we have 4.2 amps entering the junction here, remember, positive to negative. So 4.2 amps enter at this junction. That means a total of 4.2 amps should exit it as well. So in this case I have 2.8 going in this direction, 1.4 amps going through this direction. If I add them up, it should be 4.2 amps. So current entering should be equal to the current, the total currents exiting that junction. Now I have 2.8 amps coming into this junction, which means I have to have 2.8 total amps current coming out of that junction. And you can see that 1.6 plus 1.2 is 2.8. Now as the current moves to here, there will be 1.2 amps entering. I also have another 1.6 amps entering the junction. That should mean that I have 2.8 amps exiting that junction, which is exactly the same that enters that junction before it. So now I know that I have 2.8 amps going into the first junction at the top and 1.4 coming through here, which is 1.4 plus 2.8. That's 4.2 amps coming out. So it's all about playing it very, very slowly and simply. So this is series analysis, which is very easy because the current is the same everywhere. There's only one route for current to flow through, so the current will be the same everywhere. But once you start having more routes at the junction, then the current should split. So Kirchhoff's first law is a very, very important part of analyzing circuits, as well as his second law and as well as Ohm's law. But I will get to that in the next lesson when we do more about analyzing circuits. So Kirchhoff's second law. Now this law is not unlike his first law that's based on the conservation of charge. This law is based on the conservation of energy. So it says that in any circuit, the sum of EMF, electromotive force, is equal to the sum of the potential differences around a closed loop. So basically, we know that EMF is equal to the work done or the energy transferred to each unit charge. So just by looking at the definition, the fact that it's based on conservation of energy, we can already see that. So the EMF is energy given to each charge carriers, and potential difference is the work done per unit charge. So by each unit charge in the circuit. So they're both based on energy per unit charge. So what it's saying is saying that the sum of energy given by the battery should be equal to the sum of the energies given out in each component around a closed loop. So we could write an equation as well, just like we did before with Kirchhoff's first law, where we said the sum of current in a junction is equal to the sum of the currents out of that junction. But in this case, Kirchhoff's second law is the sum of electromotive force is equal to the sum of potential difference across a closed loop. That's an important part, because when we have parallel circuits, we have more than just one route. So in other words, total energy transferred to the charges is equal to the total energy transferred from the charges. A very big note here, a loop is just a single path for the current. And I have a few rules that are written down for you just to remember. If you have components in a circuit that have the same, so in a series circuit, they have the same resistance, they will share the EMF equally. If one component has more resistance in a series circuit, so for example, this is my series circuit. So if I had a 12 volts cell used, this is my EMF. Remember, whatever comes from the power supply or the battery or cell, that's the EMF. And the components share that equally, so that will be 6 volts and 6 volts. So the sum of the potential differences, 6 plus 6, the total basically, should be equal to the sum of EMFs. We only have one EMF, so 6 plus 6 should be equal to the EMF, which is 12, which is correct. Now, if one component has more resistance, so this is only if the resistances were equal of each resistor. Now, if one component has more resistance, it will get greater EMF portion, so it will have a bigger potential difference across it. Why is that? Well, if we consider that in a series circuit, what you have is the same current going through each component. So they will have, if I use Ohm's law in this case, which is R is equal to V over I. Now, if the current is the same, then all the components get the same current, so current is irrelevant. So resistance will be directly proportional to potential difference. So the higher the resistance, the higher the potential difference it will have across it. So the component with the greatest resistance usually gets the most energy per unit charge through it. One important part, again, I know I mentioned it in chapter 9, is the definition of potential difference or EMF. If you don't get that right, Kirchhoff's second law becomes hard to understand. So the last rule I wanted to talk about is if you have more than one source of EMF, meaning 2 or 3 or 4 cells connected in different ways, then you have to add the EMF in terms of polarity. So this is an example here. This is a series circuit because all of your components are connected in a single loop and current only has one single path to flow through. You have the positive, negative terminals of 2 cells connected with a total EMF of 9 volts. And then you have two more cells connected, but in the reverse way, so negative to positive. So since they're connected in the opposite direction to these cells, they have the opposite polarity. So we have to consider it as negative EMF. So what you have is E2 has a total voltage of 6.0 volts. That means that the sum of EMF, it will be equal to 9 plus minus 6, because it's in the opposite direction. So I'll put minus there, which means you have 3 volts as a sum of EMF. And then you can see the potential difference across each component. So what you have is the sum of the potential differences should be equal to the EMF. So that's 0.5 for V1 plus 1.5 for V2 plus 1.0 for V3. So that's equal to 3 volts. And there I have it. My sum of my potential difference is equal to the sum of EMF across a single loop. Now I do have a couple more examples just to make sure that we differentiate between series and parallel circuits. In this case, we have just one EMF, so the sum of EMF, which is 9 volts, should be equal to the sum of the potential differences, which is 4 plus 5, so this one and this one, which is 9 volts as well. Now, how does that work when we apply it to a parallel circuit? Well, in a parallel circuit, there is more than one path for current to flow through. So as current is flowing down this direction, it reaches a junction and it provides it with 2 different paths to flow through. That means that current will split at that junction, but the potential difference is different. So here we have current splitting, but this is Kirchhoff's first law. So Kirchhoff's first law. But when it comes to dealing with potential difference, we need to apply Kirchhoff's second law. So the sum of EMF should be equal to the sum of the potential difference across a closed loop, meaning that if I redraw this diagram actually to make it look a bit simpler, what you have is one loop and you also have another loop. So basically it's the exact same circuit as the one drawn properly, not my messy one. So yeah, these two circuits are exactly the same. So if this is one loop and the EMF is 12 volts, then across this component, the potential difference should also be 12 volts. So the sum of EMF is equal to the sum of the PD across a closed loop. Now if I take the second loop, this one, the sum of EMF should be equal to the sum of the potential difference across this loop. So 12 volts should be equal to V1 plus V2, which is 9 plus 3, which is 12. So the idea is being able to apply these two rules to circuits constantly to be able to figure out the EMF, or either the EMF, either the potential difference or current at different parts in series and parallel circuits. And also, if you notice here in this diagram, not my drawn one, you could state that the potential difference across these two parts should be, if I place the voltmeter, should state 12 volts. If I placed a voltmeter between these two parts, the voltmeter should state 12 volts too. But these two components are connected in series to each other in a parallel combination. Hence, we need to add their potential differences. So that's why I said at the very beginning that circuits are not simple like we usually expect them to be. They're not going to be just simply parallel or series. There will be series combinations in a parallel circuit. There will be the opposite. There will be parallel combination in a series circuit, and they get more and more complex. So the idea is to be able to use Kirchhoff's first law, second law, and the Ohm's law to figure out current, potential difference, and resistances in circuits. This is another example. So if I redraw this, because there's so many labels on this diagram, I will just simply redraw it. So if we look at this diagram, we can already see that we have 7 volts and 5 volts each. So this is a series circuit with a parallel combination here. Now we know current flows from positive to negative, so current I will pass through the resistor here, but then as it reaches this junction, it will split, so we'll have I1 and I2. As they meet up back again here, we're going to have I. But in terms of potential difference is what you see in this diagram as red and blue lines. So in other words, the EMF is 12 volts. Now if I go around the loop, we can split it into 2 loops. One loop can be considered to be this loop, and another loop can be considered to be this loop. So once again, the sum of the EMF for the green loop is 12 volts, and the sum of the potential difference is 7 plus 5, which is 12 volts. If I look at the blue line, it will be the same thing. So it's always about simplifying the whole circuit and figuring out how to analyze it. These are just simple examples going through it. It's not an actual question, so we will be looking at it in more depth. I thought I'd go through this one. Before I go through this one, just a quick recap. So we have Kirchhoff's first law to always remember. We have Kirchhoff's second law, which is the sum of the EMF is equal to the sum of the potential difference across a closed loop. That's very, very important, again, this part. And we have Ohm's law, which uses this equation. Just a quick mention as well here. Don't forget that the definition of potential difference is given by this equation. The definition for charge is given by this equation. Sometimes you might need to use this as well, depending on what the actual question is requesting of you to do. So just be careful that you don't forget the actual definitions for potential difference and current, which can be taken from the equations for them. So let's look at this question. It says, use Kirchhoff's laws to find the values for each current. So in this question, we can first analyze what happens to current and potential difference at each loop. So once again, I can start taking different loops. So let's take the red color for the first loop. So this is loop 1. Then we have loop 2. Then I have loop 3. So we have 3 different loops. I'll start with the what happens at each loop. So we know that the sum of the EMF should be equal to the sum of the potential difference across each loop. So V1 should be the same as EMF, because there's only one device, one component that uses the energy given by the battery. The same thing goes for loop 3 and loop 2 as well. So I know that each resistor that's in this circuit has 12 volts across them. And I know the resistance of each of the components. So if I start with first calculating the current through the first one, if I rearrange, I is V over R. So for I1, this is all to find I1, it will be the potential difference across the resistor, which is 12 volts divided by 10. So that's 1.2 amps. For I2, again, I have the voltage across it and the resistance of the resistor. So that will be 12 divided by 100, which gives me 0.12 amps. And then the last one, I3, to calculate I3 is V over R, which is 12 volts divided by 40, which will give me 0.3 amps. So I know I1, I2, and I3. And since I need to calculate the current, I2, I know that I is equal to I1 plus I2 plus I3, since the current at this junction, since I splits at this junction to I1 plus I2 plus I3, applying Kirchhoff's first law, that would be 1.2 plus 0.12 plus 0.3, which is 1.62. Yeah. Amps. Okay, so far these were just us simply applying Kirchhoff's first, second, and Ohm's law. Obviously, as you start at the beginning, this type of questions, it might be a bit overwhelming or you might not know where to go. Just remember, if you have applied these laws and you're still stuck, then obviously I can help you. But the best way is always to label each value that you have, just like I did in the diagram. I first looked at what I'm given, then tried to figure out how can that be applied, and then used Ohm's law to calculate the rest. Now the last part, well, kind of last part, is combining resistors. Now, resistors come in fixed values. So there's a resistor that could be 100 ohms, 10 ohms, 1,000 ohms, 100,000 ohms. There's some other ones as well, like 85 ohms, I think. So I don't remember every single combination, every single value that you can get. But you cannot have every single value of resistors made. They usually make fixed resistors. But when we tend to use them, if we want a specific resistance, for example, 123 ohms resistor, this is an example, by the way, there might be no resistors that have this value fixed on them. So a fixed resistor, you can't buy it and it will say 123 ohms exactly on it. So you will need to either combine them in series or in parallel in order to be able to get that value. You will be given the equations in order to calculate the series or parallel combination of resistors, but the idea is that you need to also be able to derive those equations. So we'll give you the general form of derivation, and we'll see if I can apply it as well. Okay, so let's start with series combination of resistors. I will do it with only 2 resistors, but this can be applied to in general as well. So let's call this resistor 1, resistor 2, and this equation can be expanded to more than just 2 resistors. It could be 3, 4, 5, or limitless number. So we will say that we have EMF E. This will have a potential difference since we have only one loop. So let's say this is current, I. We have V1, V2 across it. So this is the general me proving the equation. Now, when you prove these equations that we're going to see, you do need to draw these diagrams and you do need to label it so to be able to show it. So whatever I'm doing now, you should be doing too in your exams if you're asked to derive the equation. So, in order to be able to calculate the total resistance in a series circuit, we need to use Kirchhoff's first, second law, and Ohm's law as well. So from Kirchhoff's first law, we know that the current here, I, and the current going through resistor 1 and the current going through resistor 2 should all be the same. So I should be the same as I1, which should be the same as I2. This is this is an equality equation. Let's call it equation 1. Then from his second law, I know that the sum of the EMF, so I would just simply name this V for simplicity in this case. So V should be equal to the sum of the potential differences across a closed loop. So this is a closed loop, so it should be equal to V1 plus V2, since the energy here gets shared with the energy here and here. So this is equation 2. And then I also have Ohm's law, which is R is equal to V over I. Now, this equation, since I'm adding values together in terms of potential difference, gives me a hint on how to rearrange this equation depending on what variable I will substitute in there. Because I want an expression that combines resistances, not current, not voltage. I want it to combine resistance. So what I can rearrange this equation, Ohm's law basically. So this is Kirchhoff's first law, second, and this is Ohm's law. So R is equal to V over I. I will rearrange for V, which gives me with IR. Now what I will do, I will substitute that into equation 2, in the expression basically. So what I will end up with is, so I will rewrite this V is equal to V1 plus V2. If I replace V with IR in each case, so in this case it will be just the total current with the total resistance in the circuit. This is the total resistance, because this is the total potential difference here. Then I can rewrite VI as I1 R1, because we are talking about the potential difference across R1 and the current through R1 for resistor 1, plus for V2 is the resistance of R2 and the current through R2. So now I have a new expression. I will name this expression 4. And I'm going to look back at expression 1, which says that I is equal to I1, which is equal to I2. So in other words, I can rewrite all of the I1, and I2 as I, because they're all the same number. So IR is equal to IR1 plus IR2. If I divide both sides by I, so I'll take the common factor out first before I confuse you. So once again, this is the total current in the circuit, which is the same everywhere. This is the total resistance. This is the total current again, times R1. So I'm taking a common factor I out, times the resistance of resistor 1 plus the resistance of resistor 2. So if I divide both sides by I divided by I is 1. So that leaves me with the expression that that R total is equal to R1 plus R2. Now if I added more resistors and so on, that will be R plus R3 plus and so on. So this is proving that in a series circuit, the more resistors I add, the higher the total resistance gets. And you can think of it as you increasing the length of path for electrons to pass. And we know that if you increase the length, the resistance increases because then it's more energy per unit charge to pass through that wire. So we have seen that when we add multiple resistors in series, the total resistance should be equal to the resistance of each resistor added. What about when we combine resistors in parallel? How can we calculate their total resistance in the circuit? And just to remind you, we care about the total resistance because the total resistance in the circuit usually determines how much current, well, always determines how much current will be available in the circuit, and what happens to potential difference and so on. So what about if I add multiple resistors in parallel? We'll do the same thing, but instead of being in series, we'll combine them in parallel, the resistors. So this will be R1 resistor R2. And remember, I need to calculate or show a general expression of the total resistance in the circuit. I could add more resistors in parallel, but it's just going to get a bit uglier in my diagram, which is already not that clear enough. So we just stick to 2, and that's enough for the exams. So once again, I will label my potential difference as the total EMF, total potential difference in the circuit. This will have potential difference of V1 across it. This one will have potential difference of V2 across it, current of I2 going through it, and a current of I1 going through it, and a total current in my circuit of I. Let's start with Kirchhoff's first law again. The sum of currents going into a junction, so I should be equal to the sum of the currents coming out of that junction, I1 plus I2. Then we go to our second expression, which will be in terms of potential difference. The sum of EMF, which we called V, should be equal to the sum of the potential difference across a closed loop, which is V1 only, and the same thing for this loop, which is V2. So I have 2 expressions. I need Ohm's law 2. But in this term, the values that I'm adding together is current, not voltage, potential difference like we did with the series circuit. So I will rearrange for I and not V, because V is not a real equation. It's more of an equality of that all values of V should be the same. For simplicity, I will label all potential differences as V, since they're all the same as well. So I will rearrange this equation for I. So I is V over R. So if I do the calculation, it will be, if I now substitute this expression into equation 1, then I will have for I, let me just rewrite it. So I will be total EMF divided by total resistance, which is equal to the EMF or total potential difference over resistance 1 plus total EMF over resistance 2. I will do the same thing. I'll take a common factor out, V, and if I divide both sides by V, V divided by V is 1, so I'm left with 1 over R is equal to 1 over R1 plus 1 over R2. If I had more resistors, then it will be 1 over R3 plus so on. When you calculate the total resistance in a parallel circuit, the most common mistakes that people forget to inverse their answer that they get from doing 1 over R1 plus 1 over R2 plus 1 over R3 They forget to do 1 over their answer because the answer that you get is 1 over r. So it should be in reality coming up to. So when you put in your calculator, it should look like something like this to make sure that you get the r instead of the 1 over r answer. Okay, so I know this video is getting a little bit too long, but we need to do a lot of examples in these questions. Otherwise, you won't get it. The more the practice, the better. So it's just a very quick way of combining resistances. For example, if I wanted to know the total resistance in this circuit here, I have a 4 ohm resistor connected to a parallel combination of 6 ohm and 3 ohm resistors. So first we will need to deal with this combination. So I can replace a 6 ohm and a 3 ohm resistor with that are in parallel with one resistor. The resistor will have a lower resistance of the lowest resistance of the two. So I will show you through the calculation. So the total resistance of this combination here will be 1 over 6 plus 1 over 3. If you do that in your calculator, so this gives you a half as an answer, but that's equal to 1 over r total, which means you need to flip the expressions upside down. So r total is equal to 2 ohms. So the total resistance you can see of this parallel combination is less than the least amount resistance that it has. And now I can redraw the circuit. It will be a 4 ohm resistor connected to a 2 ohm resistor, which is the parallel combination that we just proved. And since they're in series, R total is 4 ohms plus 2 ohms, which is, I used this R1 plus R2, which is 6 ohms. And I can use this value as well if I wanted to calculate the current in the circuit, the total current in the circuit. It gave me the voltage here. Let me erase that. So it gave me the EMF. So the total EMF of the circuit, and I know the total resistance of the circuit, which means I can calculate the total current in the circuit. So I will be V over R, which is 24 divided by 6. So it will have 4 amps of current coming through here. So 4 amps will go through this component, but then it will split, and you can even calculate how much each parallel combination will have across it. But this is something that we'll talk about in the next lesson. Then we have the second circuit here. Now this is a series and parallel combination within a parallel combination. So you need to break it down slowly. Usually we deal with the parallel combination, then with the series of the parallel combination, then the whole parallel combination. So in this case, for this part, we'll have 1 over r total is equal to 1 over 220 plus 1 over 220. This gives us a total resistance of 110 ohms. Now, if I replaced this with a single resistor, it will be 110 ohms. So I'll redraw my circuit. This is 110 ohms with the 220 resistor next to it, connected in parallel to a 220 ohm resistor. Now these two are in series, so I just simply need to do R total is equal to 110 plus 220, which gives us 330 ohms. So I can replace these two now with a single resistor of 330 ohms, which is connected to, once again, the same resistor of 220 ohms here. And now I have a parallel combination, which is 1 over 330 plus 1 over 220. So the total resistance of this combination will be 132 ohms. So if I could replace all of these resistors here with a single resistor, it would be 132 ohms. But there's no resistor that has 132 ohms exactly, so it has to be combined in a different way like this to get them. Then we have this diagram. I will go through it. I'll just redraw it somewhere else. Okay, so this could have been a simple question as calculate the value of IT, I1, and I2 in the circuit diagram. It gives us all the resistances and it gives us the potential difference of the power supply. So remember these circles here mean power supply. We usually see it drawn as this. It doesn't matter how far they are. This is the same thing as this. So the EMF is 12 volts. That means that if I redrew this diagram, it has a series component connected to parallel. So I will redraw it just to make a bit more sense of it. It will look like, actually let me redraw it in the diagonal way. Always if you ever get confused, you need to remember that you can redraw circuit diagrams to the way that they make sense to you. So it will be terminal A here connected to R1, which is 6 ohms, which is then connected to a parallel combination of R2, that's 8 ohms, and R3, that's 4 ohms, and then that's parallel connected to R4, which is 12 ohms, and that's connected to the other end of the power supply, B. Now I know that the potential difference between A and B should be 12 volts in total. The easiest thing to do when we start first is to calculate the total resistance, because that way it can help us find the total current. And from the total current, I can find I1 and I2 afterwards. So, total resistance in the circuit. We will start with the combination of these two, then of R2 and R3. Then we're going to combine it with R4, and then we'll combine it with R1. So, since they're in series, R2 and R3 are in series, is 8 plus 4, which gives us 12 ohms. And then I have 12 ohms in parallel with 12 ohms. So in other words, I'm left with this. So that will give me a total of 6 ohms. So now I can replace all of this combination with a 6 ohm resistor. So it will be 6 ohms with 6 ohms. So the total of that will be, since they're in series, 6 plus 6, which is 12 ohms. So I know the total resistance of my circuit and I know the total EMF. So that's my EMF and that's my total resistance in the whole circuit. I can find the total current, so the IT that we said. So that would be I total is V total over R total, which is 12 divided by 12, which gives us 1 amp. So this current here is 1 amp. So we have 1 amp entering here and it splits into two, into I2 and I1. I can't proceed from here unless I calculate how much potential difference is across this resistor. Because if I look at the diagram I drew here, I know that the current entering it is I total, which is 1 amp. So I know that 1 amp is going through resistor 1. But then I know that that current splits here into what did they label it there? As I1 and I2. So that's I1, I2 going through here. For me to be able to calculate how much current goes through each loop, and by the way, this is a hard question in a way that it's the first time you see something like this, so don't panic too much through it. It's better to see the harder and then work through the easier stuff. So I know the current going through there and I know the resistance, so I can calculate easily the potential difference across that resistor. And to do that, we know that R is V over I. So V across 1 should be I1 times R1, which is 1 times 6. So the potential difference across resistor 1 is 6 volts. That means that between this junction and this junction, the potential difference is also 6 volts. So this component here, since it's on its own, gets a full potential difference of 6 volts. So 6 plus 6 is 12, remember that? So that's one loop. So this is the one loop, and this is the second loop here. So what I have is, I can calculate I2 because now I have the potential difference across resistor 4 and the resistance across resistor 4. So I2 is equal to potential difference across resistor 4 divided by the resistor 4, which is 6 over 12. So that's a half amps. Sorry, 0.5 amps. We don't like fractions in exams, so please don't leave anything in fractions. So yeah, that's 0.5 amps. So if 1 amp enters, going back to this diagram, since I have 1 amp entering here, then and half of it goes here, that means I should have half as well. Obviously, do not panic through these questions. Slowly break them down. Label your diagrams like I'm doing, and we will go through more of this in class. If you do have questions, let me know, and do go through this question again slowly and try it on your own as well to get more grips and more confidence through it. So going back to the learning outcomes, we have looked at Kirchhoff's second law. We applied first and second law to circuits. We proved the total resistances, how to calculate them. We have looked at analyzing circuits that are both in series and parallel. And we have looked at one example of how to use more than one source of EMF, but we will obviously do more questions in class that will apply all of this content.